Welcome, curious minds, to another deep dive. Today we're jumping into something from general mathematics, sequences and series.
Yeah, and if those words just make you think of, like, old dusty textbooks.
Right, prepare for a surprise.
Yeah.
Because these ideas, they're actually woven into so much of our daily lives. Think algorithms, music, even, how populations change.
hmm
Okay, let's really unpack this. So our mission today, we want to pull out the really key ideas about sequences and series. No jargon, just demystifying them.
Getting to the core of it.
Exactly. And show you how they're kind of a shortcut to understanding patterns and sums all around us. You might have a few aha moments, hopefully.
Well, what's truly fascinating here is how fundamental these concepts are. They're tools, really, for understanding how things change over time.
Growth, decay, that sort of thing.
Precisely. Growth, decay, simple progression. You see them everywhere. Science, finance, engineering. Even art uses these patterns. They give us a way to model things, maybe even predict them.
Okay, so let's start right at the beginning then. What is a sequence, actually?
Well, simply put, it's just an ordered list of numbers,
Okay.
and crucially, they follow a specific rule or pattern.
Like, 2, 4, 6, 8, 10. Even numbers. That's a sequence.
That's a perfect example, and
Yeah.
see how this stops.
Yeah.
That makes it a finite sequence.
Okay. Finite. Got it.
But if you put those three dots at the end,
Yeah.
2, 4, 6, 8, 10, like that,
The ellipsis.
that
Yeah.
means it goes on forever. And that's an infinite sequence.
Finite stops, infinite keeps going. Makes sense.
And mathematically speaking, we define it as a function where the domain is integers.
Okay, hang on. Domain.integers. What does that really mean in simple terms?
Right, good question. Think of it like this. Every number in the sequence has a position. First, second, third, right.
Uh-huh.
We call it position n. The rule, maybe something like an ellipsis n, tells you how to calculate the value for any position n.
Ah, okay. So n is the position, n is the actual number in that position.
Exactly. N is the domain first, second, third, and n is the range, the values 2, 4, 6, etc.
So it's basically a set of instructions, step-by-step number building.
You got it.
And once you get that, you can do some useful things. Like if I give you a rule, say n equals 12 and 3, you can just plug in n1 and n2 and reads 3 and crank out the terms, right?
Yep. Pretty straightforward.
But what about the other way? That sounds trickier. If I give you like 3.1, 3.8, 4.5, 5.2 and say, find the rule, how do you even start?
That's where it gets interesting. It's a bit like detective work.
Looking for the pattern.
Exactly. Look for patterns.
Yeah.
Is something being added each time? Multiplied? Maybe try a little guess and check. And if you see fractions, sometimes it helps to look at the numerators and denominators separately. Find their patterns.
Okay, detective work. I like that.
Now, let's talk about graphing these. It looks a bit different.
Different how?
Well, you treat n the position like your x-axis and the value like your y-axis. But the graph is just dots, distinct points.
Just dots, you don't connect them.
Absolutely not. You do not connect the dots. And that brings up a really important question. Why do you think it's just dots? Why not a smooth line?
Okay, well, you said the domain is integers, so n can only be 1, 2, 3 whole numbers.
Right.
So you can't have a term in between, like a 1.5th term. So the graph can only exist at those specific whole number spots.
Precisely. Perfect analogy.
Yeah.
Think about your height. You have a height on your first birthday, second birthday, third, but not on your, 1.5th birthday, right?
Yep.
It doesn't make sense. Sequences are like those birthday snapshots. Values only exist at those integer points n. So dots never align.
Got it. Discrete points. Okay, that makes sense. So we have these ordered lists, sequences, mapping out patterns point by point. But often it's not just about the individual steps, is it? It's about the total effect. Like, what do they all add up to?
Right, the cumulative impact.
Yeah, and that's the jump from a sequence to a series. It's about the sum. So 2, 4, 6, 8, that's the sequence.
And 2 plus 4 plus 6 plus 8 plus there.
That's the series. We're adding them up. This is where it gets really interesting for me.
And to write these sums down, especially if there are loads of terms, we use summation notation, sigma notation.
Ah, the big Greek letter sigma.
Exactly. It's got three main parts. The number on top is the upper limit where you stop adding.
Okay.
The number on the bottom is the lower limit where you start. And then there's the index of summation, usually an I or n, which is the variable in the formula you're summing.
And series can be finite or infinite too, just like sequences.
Yep, absolutely.
Yeah.
Depends on whether you stop adding or keep going forever.
So you might need to do things like take a sum, maybe 7 plus 10 plus 13 plus 16 plus 19, and write that using sigma notation.
You might, or the other way around, you might be given something like the sum from I2 to 8 of 2i.
And then you have to actually calculate the total sum. Plug in I2, I3, all the way to 8 and add them up.
Right. But doing that manually for, say, 100 terms, that gets tedious.
Oh, yeah.
So luckily, there are some really neat shortcut formulas.
Yes. Shortcuts are good.
For example, the sum of just the number 1 from I1 to n is simply n.
Okay, that makes sense. 1 added n times is n.
And the sum of I itself from 1 to n. That's nn plus 1, 2.
The famous Gauss formula.
Well, related to it, yes.
Oh.
And there's one for I2 as well. nn plus 1, 2n plus 1, 6.
Wow, okay.
These formulas are lifesavers. Say you need the sum of I, but starting from I10 up to 25, you could use the formula to find the sum from 1 to 25, then find the sum from 1 to 9, and to subtract the second from the first much faster.
Clever. Avoids adding up all those numbers individually.
Exactly. It really shows the kind of elegance of math, right? Finding these patterns to simplify complex calculations.
Okay, so let's focus on one specific type now. Arithmetic sequences and series.
Right. Arithmetic. The key here is the common difference. We usually call it D.
Common difference, meaning?
It just means you add the exact same value each time to get the next term. Or subtract, which is just adding a negative.
Okay, like 3, 6, 9, 12, 15. What's the common difference there?
Well, you're adding 3 each time, so D3.
Right. Simple enough. Okay, here's one for you listening. Menic 10, Menic 6, 0, 2, 6, 10. Is that an arithmetic sequence? Take a second.
What do you think? Look at the jumps between terms.
Let's see. Menic 10 to Menic 6 is plus 4. Mega to 6 to 9 to 2 is plus 4. But mega to 2 to 0 is only plus 2.
Bingo. The difference isn't common. It changed. So, nope, not an arithmetic sequence.
Gotcha. It has to be constant.
Exactly. And for these arithmetic sequences, there's an explicit formula for the nth term. And A1 plus N1D.
A1 is the first term, D is the common difference, N is the term number.
Precisely. And if you look at that formula in A1 plus N1D, it's actually a linear relationship. It makes sense, right? You're adding the same amount repeatedly, like points on a straight line.
Yeah, that makes sense.
So with this formula, you can figure out the rule for a sequence like 51, 48, 45, 42.
Okay, the difference is Menic 3.
Right. Or even if you're just given clues, like, say, the 8th term is 50 and the common difference is 0.25, you can find the rule.
Or even just 2 terms, like if A5 equals 10 and A30 equals 1 and 10.
Yeah, you can use those 2 points to figure out the common difference D and then work back to find A1. It's like solving simultaneous equations, almost.
This whole thing reminds me of that story about Carl Friedrich Gauss, the mathematician.
The summing 1 to 100 story?
Yeah.
Classic.
Yeah. His teacher asked the class to add up all the numbers from 1 to 100. Probably just to keep him busy, right?
All right, give himself a break.
And little Gauss supposedly figures it out in, like, minutes. He paired them up. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101.
All the way to 50 plus 51, which is also 101.
And how many pairs are there?
Well, from 1 to 100, that's 100 numbers, so 50 pairs.
So 50 pairs, each adding up to 101. 101 equals 50, 50. Boom. Done.
Brilliant, kid. Just brilliant. What a great insight into pattern recognition.
Totally. And that insight directly connects to the formula for the sum of a finite arithmetic series, doesn't it?
It does. The formula is Sn A1 plus N2.
So n is the number of terms.
A1 is the first term, n is the last term. Notice the A1 plus n part. That's like Gauss's pairing, finding the sum of the first and last. And N2 is like the number of pairs.
I see the connection now. That's elegant.
So we can use this formula to find the sum easily. Like, find the sum from I1 to 20 of 2I3. First find A1 and A20, plug them into the formula with n at 20.
Okay, let's try and make this concrete. Imagine a money jar. You put $2 in the first week.
Okay.
Then the next week, you put in $2 more than the week before. So $4. Then $6, then $8.
An arithmetic sequence with A1 equals 2 and D equals 8.
Exactly. So first question for you listening. How would you write the rule, the explicit formula in, for the amount you put in during the nth week?
Using A1 plus N1D.
Right. And then the bigger question, what's the total amount of money in the jar after, say, 9 weeks?
For that, you'd use the sum formula, S and N, find A9 first, then use S9 equals 9, A1 plus A9 2.
See, this applies directly to things like savings or tracking any kind of steady linear increase. It lets you predict the total outcome.
Absolutely.
Okay, so that's arithmetic. Adding, what's the other main type?
Geometric sequences and series.
Geometric. And the key difference here is,
instead of adding a common difference, you multiply by a common ratio, usually called R.
multiplying. Okay, so like the sequence 96, 48, 24, 12, 6, what's happening there?
Well, each term is half of the previous one.
So you're dividing by 2, which is the same as multiplying by.
Multiplying by 12 or 0.5. So the common ratio R is 12.
Got it. So R can be a fraction, less than 1.
Oh, absolutely. That leads to decay. Like in this example, if R is greater than 1, you get growth.
And there's an explicit formula for the nth term here too, right?
Yep. It's an A1R N1. Notice the N1 is now in the exponent.
Ah, r raised to the power of n1. That signals exponential change, doesn't it?
Exactly. Geometric sequences model exponential growth or decay, things that grow really fast or shrink quickly based on a percentage.
So with this formula, we could write rules for sequences like 112, 56, 28, 14.
Yep. Find R first, which is 12 again.
Or if we're given, say, A4 and R equal 3.
Plug them into the formula A4 equals A1R 4 to 1 and solve for A1.
And that, again, even if we only know two terms, like A2 equals 4 and A6 equals next and over 124.
It's a bit more work, but yeah. You can set up two equations using the formula and solve for A1 and R. Usually involves dividing the equations to eliminate that.
Okay, so similar logic to arithmetic, just with multiplication and exponents involved.
Pretty much.
And naturally, there's a sum formula for finite geometric series, too.
There is. Adhere Sn equals A1, 1R and N, 1R.
Looks a bit more complex with the powers and fractions.
It is, but it works the same way. You need the first term A1, the common ratio R, and the number of terms N. Plug them in.
So if we had, like, the sum from I1 to 8 of 5, 13, I1,
Yeah.
identify A1, 5, R13, N8, and just plug those into the formula.
That's exactly it. Calculate carefully, especially with the fraction and exponent, but it gives you the sum directly.
Let's think about a real-world example for this one. Spreading information.
Oh yeah, perfect example, geometric growth.
Okay, imagine you tell 4 friends some big news. Then each of those 4 friends tells 4 new friends, and each of those tells 4 more, and so on.
The number of newly informed people in each round is growing geometrically. Round 1 is 4 people. Round 2 is 44, 16. Round 3 is 164, 64. The common ratio is 4.
Right. So if this keeps going for, say, 8 rounds, how many people in total have heard the news? Starting from you telling the first 4.
That's a finite geometric series sum. A1 is 4, the first group you told. R is 4, and N is 8 rounds. You'd use the Sn formula.
And the numbers get big fast, don't they?
That's the power and sometimes the danger of exponential growth. It really highlights how quickly things scale up with a multiplicative factor.
Okay, deep breath time. Because now we're heading into slightly weirder territory.
Yeah. Infinite series.
Infinite geometric series, yeah. The idea of adding up an endless list of numbers, it just feels wrong somehow. Like, shouldn't the answer always be infinity?
It really does feel counterintuitive. How can adding forever result in a finite number?
Let's use that classic visual, the pie.
The pie, we're walking across a room.
Yeah. Okay, the pie. You eat half the pie, 12. Then you eat half of what's left, which is 14. Your total eaten is 12 plus 14 is 0.75.
Keep going.
Then half of that remainder, 18. Total is now 0.875. Then 116, total 0.9375. Then 132, 164.
Notice what's happening to the total sum.
It's getting bigger, but it's getting closer and closer to 1. It seems like it's approaching 1.
Exactly. It's converging towards 1. So the question is, if you could actually continue this process forever, what would the sum be?
It feels like it has to be 1. You're eventually eating the whole pie, just in infinitely smaller slices.
You'd be right. Sometimes you can get a finite sum from an infinite geometric series.
Okay. How?
Yeah.
Is there a formula?
A surprisingly simple one, actually. The sum S is just a 1, 1R.
Wait, that's it. First term divided by 1 minus the common ratio.
That's it. This is where it gets really interesting, like you said.
Yeah.
Adding forever can land you on a specific number.
But there must be a catch. It can't work all the time, right? What if R was like...
You've hit the crucial condition. This only works if the absolute value of the common ratio R is strictly less than 1, so R1.
Meaning R has to be between -1 and 1, but not including -1 or 1.
Exactly. If R is 1 or bigger, the terms either stay the same size or get bigger, so when you add them infinitely, the sum just blows up to infinity or doesn't settle down, it diverges.
So for our pi example, A1 equals 12, R equals 12. Since 12, 1, the formula works. S112 equals 1. It works.
See, simple formula, profound result.
Let's apply this. A pendulum. You pull it back and let it go. First swing is, say, 100 centimeters.
Okay.
But each swing after that, because of friction and air resistance, it only travels maybe 96% of the distance of the swing before it.
So the common ratio R is 0.96, and A1 is 100.
Right, and 0.96 is less than 1. So even though theoretically it swings infinitely many times, getting smaller and smaller,
We can find the total distance it travels before it essentially stops using the infinite sum formula.
S equals A1, 1R, equals 100.96 equals 100.04. What's that? 2,500.
That's right, 2,500 centimeters. That's the total path length.
Wow, okay, that's cool. Calculating a total for an infinite process.
And here's another really neat trick with this, repeating decimals.
Like 0.3333 or something more complex.
Yeah, take 0.272727, for example.
Oh.
You can actually think of that as an infinite geometric series.
Oh.
Well, it's 0.27 plus 0.00027 plus 0.0000027 plus... Right.
I see the pattern.
The first term, A1, is 0.27. What's the common ratio R? What are you multiplying by each time?
To get from 0.27 to 0.00027, you multiply by 0.01 or 1100.
Exactly. R.20 is R1.
Yep, 0.01 is definitely less than 1.
So we can use the formula.
Yeah.
S equals 0.27, 1.01, 0.99.
Okay, 0.27 over 0.99. That simplifies, right? Multiply
Yes.
top and bottom by 100 gives 2799.
Then 27 and 99 are both divisible by 9.
Ah, so it's 311. So 0.27272727 is exactly equal to the fraction 311.
Isn't that cool? Using infinite series to convert repeating decimals into clean fractions.
That is seriously clever. Okay, so we've done explicit rules where you find in directly, but there's another way to define sequences, right?
Mm-hmm. Recursive rules.
Recursive. How's that different from explicit?
Okay, an explicit rule, like in Hansi 2 plus 4n, lets you jump straight to any term. Want the 100th term, plug it in 100. Done.
Right. Direct calculation.
A recursive rule doesn't do that. Instead, it tells you how to get the next term based on the previous term. It defines in terms of an1.
So you need a starting point.
Exactly. You always need the first term, or sometimes the first few terms,
Yeah.
defined explicitly. For example, a1 is 6, and then the rule and 1 plus 4.
Ah, okay. So A1 is 6, then A2 is A1 plus 4, which is 6 plus 4 equals 10. A3 is A2 plus 4, so 10 plus 4 equals 14. You have to build it step by step.
Precisely. You generate the sequence iteratively. Like if I gave you a1 equals 3 and an and of 1, 1.
Okay, A1, 3, A2, A1, 1 equals 23, 1 equals 5, A3 equals 2, A2, 1 equals 4, 1 9, A4 equals 29, 1 equals 17. So on.
You got it. Now notice our first recursive example, and a and 1 plus 4. That's just adding the common difference d4 each time.
Oh, right. So arithmetic sequences have a simple recursive form,
Yeah.
n and 1 plus d.
Yep, and guess what the recursive form for geometric sequences is?
Geometric is multiplying by r. So the current term is the previous term times Rn equals Ran1.
Perfect. So you have these nice, neat recursive definitions for both types. Now this raises an interesting question. Why bother with recursive rules if explicit rules let you jump straight to the answer? Why might recursive be more natural sometimes?
That's a good question. Maybe because lots of things in the real world actually do depend directly on the previous state, like population growth depends on the current population, or compound interest depends on the current balance.
Exactly. You're thinking about dynamic systems, feedback loops, situations where what happens next is a direct function of what's happening now. Recursive rules often model those step-by-step changes much more intuitively.
So it's like two different languages for describing patterns, and sometimes one language fits the situation better than the other.
That's a great way to put it. And being able to translate between them is a really useful skill.
Translate, like take an explicit rule and write it recursively, or vice versa.
Yeah. For example, let's say you have an arithmetic sequence with a1 equals 15 and d equals 5.
Okay. Explicit rule is n equals 15 plus n1 5, which simplifies to n equals 10 plus 5n.
Right. And the recursive rule.
Well, you need the start, a1 equals 15, and the rule is just an an1 plus 5.
Easy enough. Now, geometric. Say a1 and r equals 0.2.
Explicit, n equals 4, 0.2, and x1. Recursive, a1 equals 4, and it equals 0.2, an1.
Perfect. Now, slightly harder. Convert an explicit rule like it equals 35n into a recursive one.
N equals 35n. Let's find the first term. a1 equals 35, 1 equals 25. What about the common difference? If I find a2 equals 35, 2 equals 20, the difference is 20, 25, so d equals minus 5.
Let's try.
So the recursive rule would be a1 and x is 25 and an an1 5.
Nicely done. Last one. Convert a recursive rule, say a1 equals 2 and an equals 3 and s1, into an explicit one.
Okay, a1 is equals 2. The rule next to 3an1 tells me it's geometric with r3. So the explicit formula isn't a a1rn1. That's just an a equals 2, 3n, and s1.
Excellent. So you see how you can move between these two ways of describing the same sequence.
Yeah, depending on what you need to do it.
And this recursive thinking is super useful for modeling more complex real-world stuff.
Like what? Give me an example.
Okay, imagine a lab. You start with, say, 500 mosquitoes.
Okay, lovely.
Every day, 100 new mosquitoes hatch. But also, every day, 85% of the total population dies off due to pesticides, old age, whatever.
Wow, okay. 100 added, but 85% removed. That's dynamic.
Very. So how would you write a recursive rule for mn, the number of mosquitoes at the start of the nth day? Let m1 equals 500.
Okay, mn, the number on day n, depends on mn1, the number on the previous day.
Right.
So you start with mn1, then 85% die off, meaning only 15% survive. So that's 0.15 mnn1.
Good start.
But then 100 new ones hatch. So you add 100 to that surviving population.
So the rule is?
mnn equals 0.15 mn-1 plus 100, with m1 equals 500.
Perfect. See how the recursive rule captures that step-by-step change naturally?
Yeah, it does. And then you could use this rule to find the population on day 2, day 3, day 4, just by plugging in the previous day's number.
Right. You could calculate M4. And you could even investigate what happens to the population over a long time. Does it stabilize? Does it die out? Does it grow forever?
Interesting. It feels like it might stabilize somewhere, with the loss balancing the game.
It often does in systems like this. It approaches a limit. Another great example is loan payments.
Oh yeah, recursion and finance seem like they go hand in hand.
Definitely. Say you borrow $2,000. The interest rate is 9% per year, but it's compounded monthly.
Okay, so you need the monthly interest rate 0.09, 12, 0.00075.
Right. And your monthly payment is fixed at, say, $91.007 for 2 years.
Right.
Let Bn be the balance after the nth payment. B0 is $2,000.
Okay, so the balance after payment, NBN, depends on the balance before that payment, which was related to BN1.
Now, what happens each month?
Well, first, interest is added to the previous balance. So you take BN1 and multiply it by 1 plus 0.0075.
That's a balance including interest.
Then you make your payment. So you subtract $91.775.
So the recursive rule for the balance after payment N is?
BN dash 1.00075, 91.37, with B0 is 2,000.
Exactly. And using this, you could calculate the balance after 5 payments, B5, or figure out the amount of that very last payment, which might be less than $91.37.
It really models the step-by-step process of paying down debt.
It does. So connecting this to the bigger picture, recursive rules are just indispensable for these dynamic systems, populations, finance, computer algorithms, physics simulations, anything where the state evolves based on the previous state.
Wow. Okay. We have covered a lot of ground. Sequences, series, arithmetic, geometric, finite, infinite sums, explicit rules, recursive rules.
It's a whole toolkit.
It really is. And hopefully you listening can see that this isn't just abstract math. Understanding these concepts gives you real tools to analyze patterns, make predictions, maybe even solve problems you encounter. So what does this all mean for you?
Well, my final thought, maybe a little challenge for you, is to start actively looking for these patterns in your everyday life. Now that you know about arithmetic and geometric progressions, about common differences and ratios, where do you see them?
Like watching investments grow, or?
Or maybe how quickly news spreads, or how medication concentration decreases in your body, or even patterns in nature or music. Once you start looking through this mathematical lens,
You start seeing the underlying structure.
exactly, the world might start to look a little less random, a little more patterned. There's always more to learn when you recognize those structures. It's like seeing the code beneath the surface.
A fantastic way to put it. See the code. Well, thank you for joining us on this deep dive into sequences and series. Keep that curiosity going.
Keep looking for those patterns.
Meet you next time.